Engineering College, Katihar. It's my immense pleasure to introduce Dr. Bikash Chandra Sahana sir. Dr. Bikash Chandra Sahana sir is currently working as Assistant Professor and Head in the Department of Electronics and Communication Engineering, National Institute of Technology, Patna. He has completed his BE from University of Burdwan in 2002 and ME from BIT Mishra in 2004 and PhD from NIT Patna in the year 2018. He has 17 years of experience of teaching and research. He has plenty of publication in SCI journals and conferences in last 3 years. His main area of research include biomedical signal processing, radar signal processing, geophysical signal processing, image processing, wireless communication, adaptive filters, machine learning, and IoT. He is reviewer of journal IEEE computing and digital systems, and also visited different countries like South Korea, UAE, and Romania for conferences. He's also delivered various invited lectures across the globe. So thank you, sir. Now I request Bikash Chandra sir to start the session. Over to you, sir.
Thank you, Dr. Rasid, for giving me opportunity to interact with the faculty members in today's session of FDP. In this FDP, most of the topics are related to image processing, medical image processing. But in today's session, I would like to deliver the artifact removal techniques from EEG signal using machine learning and other statistical techniques. In this session, we'll learn some basics of EEG signal because it requires some background. That's why in initial PPT, we'll go through motivation for doing this kind of research work. The second thing, background of EEG, since this FDP is oriented on image processing, so background of EEG is required. Second thing, different techniques which can remove the artifact from EEG, right from basics of filtering technique to machine learning. These things would be covered through this presentation. That is my aim. Now let me share the PPT. Title of today's talk is Artifact Removal of EEG Signal using Machine Learning Techniques. Before going to that, let us discuss about some applications, and next we'll move to your artifact removal. Nowadays, different wearable devices are available which can extract EEG information, and it is useful for different brain your computer interface applications. Apart from that, EEG signals are very much useful for diagnosis of different neural disorders. It requires long-term recording of multi-channel EEG signals. During this recording process, different noise or artifacts introduced in the process, and your pure EEG signal becomes noisy. So today's lecture main aim is to know about what are the artifacts are present in EEG signal and how to remove your noise or artifacts from multi-channel EEG signals. multi-channel EEG signals. Now, these are the some company which manufactures different wearables. These are well-known and world-renowned companies. Manufactures your different wearables and your EEG devices. Next, you see different smartphone apps are also available. By integrating your different sensors, EEG sensors, you can track the EEG, your records. You can monitor the EEG records for long time, and it is useful for data analysis purpose. After analyzing the EEG data, a doctor can suggest suitable solutions or can give you proper treatment to the neurological your different disorders, people with different neurological disorders like your Alzheimer, your hyperactivity in children, sleep disorders, so many your neurological disorders are there, and it can be properly diagnosed with the help of your this kind of multi-channel EEGs. Now, these are the some application. Let me skip this challenges. Now, what is the challenges of this IoT kind of devices? It's having your latency. By after acquiring the data from EEG sensors, those data are pre-processed and sent to the server through your LAN or different networks. Afterwards, effective analysis of data is required, and based on those analysis, your final recommendation being made by the doctors. So it takes your long time to reduce this your long time cycle. If we put your machine learning part within the sensor, so we can remove the artifact, and our IoT devices would be more very much smart, and it will reduce the latency. And doctor can also get the your analyzed data, your artifact-free data quickly, and can give your solutions quickly. These are the future monitoring and quick decision by introducing your modern artifact-free your technology for removing your noise from EEG. We can give your quick decision and quality user experience. We can give remote monitoring of patient can be feasible by introducing this modern technique. Now, what is your scope of improvement? That is your response time, energy consumption, cost effectiveness, reliability, security, throughput. So many your lists are there. Your improvement, your chance of improvement, scope of improvements are there. Now, this is your generalized your block architecture of wearable IoT sensing. So here, what do you do? We collect the data from hospitals or social network or different sensors placed with this your patient, and after that after collecting data collection, what do we do? It's sent to the cloud, and afterwards data analytics is being done. So during this process, it involves your several steps like your data pre-analysis, data processing, feature extraction, dimensionality reduction, and afterwards your training and testing methods are there in machine learning, and based on your final findings, we do your diagnosis and recommendation. This is your whole process. If you look into central block, in conventional your machine learning technique like your SBM or a simple artificial neural network, it's having two pages, one your training page and second is your testing page. In training page, we all know who works in this machine learning area, it requires you some data pre-processing followed by your feature extraction. Afterwards, suppose if your feature length is your more, in that case, we use dimensionality reduction techniques like your principal component analysis or something like that. And afterwards, we do your training process and we do your several tuning in training. And afterwards, we do testing for getting the efficacy of this method. So here, our purpose is to use your machine learning for denoising. In several applications, we use machine learning for classification job, and here our purpose would be classification and your noise removal in both the cases. Classification in the sense, suppose you have one pure EEG signal and you have your some artifact, your accumulated noisy EEG signal. So first challenge would be how to identify these artifacts. That would be the first challenge. And after classifying the artifacts or noise, your added signal, we have to remove the noise using machine learning techniques. So two kind of work can be done. First is your identification of artifacts, followed by your denoising operation. So in literature, if you look into, so many techniques are there for removal of this kind of artifacts, but you will find some literature for denoising and classification purpose for EEG signal. Now this is your more your detailed architecture. Here not only your sensor data, in addition to social networking data also being incorporated for taking your final decision, whether a patient having Alzheimer's disease or not, whether a child is hyperactive or not, whether any particular patient or person having your sleep disorder or not. So you see, social networking data is also incorporated in this case. So what is that basically? Social networking data, like a particular person is very active in social networking, that means it indicates his health is, there's no that kind of issues with the health of that particular person. Suppose if any person is suffering from your Alzheimer, so that person would not be that much active. Suppose a particular person having that kind of data, your symptoms in EEG, and also from social networking, it says that particular person is not active for long time. So it will cross-verify the thing and doctor can take final decision. So this kind of aspects are coming nowadays. Yeah, scientists are not dependent on your sensor data. They are also incorporating your social networking, your activities also before taking your final decision. Afterwards, if you look into this flowchart, here it gives your more detailed view from where we can get the data. Standard your database are available free database as well as paid database are available. And if you collaborate with different your hospitals for research purpose, you can get the data. So data can be from wearable devices or sensors. It can be medical records from hospital, or it may be social networking content, or it may be drug review from different your companies who manufacture medicines related to neurology. Now, from those data, uh, you need to pre-process like your artifact removal, noise removal, unsupervised filtering kind of thing. It may be adaptive filtering. So, in today's lecture, our main concern would be pre-processing part, and it is very much vital. And one precaution is that we have to take care during your pre-processing stage. We have to use your these filters or noise removal techniques in a very smart way, such that important medical information it preserves. Through filtering process, important medical information may be your cut out, but you have to take care such that important information should not deleted. So that is a major challenge in this work. And artifact is different type, not a single type. The different variety of artifacts are available, and it lies within different frequency bands, wide frequency band. So you need to identify the correct artifact, and afterward removal techniques you have to apply for that. So a single your technique, it is very difficult to devise a single technique by which multiple artifact can be removed. If you use your statistical or your different your statistical filters. But nowadays, current trend is to use your deep neural network or your different CNN, convolutional neural network, for removal of those kind of artifacts by introducing different layers in between and different combination of filters, convolutional filters, which can extract your this actual behavior, actual feature of your signal, and can remove the signal, remove the your noise part. For that, one your objective function need to be introduced. So in latter part of discussion, we'll see how with the combination of your CNN, convolutional neural network, and some objective function for minimization of your error, your complete algorithm can reduce the noise or artifact of EEG signal. So this is your conventional technique, pre-processing followed by feature extraction, followed by dimensional reduction, and machine learning. If you want to use, you can use. Like here in this diagram, they have used LSTM technique. LSTM technique is widely used in the literature, and nowadays your CNN lot of paper with convolutional neural network and its variants, different variants are coming up. So since it is your one-dimensional signal, EEG is your one-dimensional signal, multi-channel one-dimensional signal. So using your very simple configuration of your CNN, you can sort out your artifact problem, which gives you a better efficacy with respect to your conventional statistical your filters. Now, this is your these slides I have given you for motivation. How we should, why we should learn this particular topic. And this topic is quite vast. We have limited time to I'll try to cover the fundamentals and some case studies such that if you have special interest, you can carry out research in this area. Now, after what is the outcome of machine learning? Machine learning can be used for denoising purpose and for classification purpose as well. Here you see, here it is mentioned, present classification has been done with the help of machine learning. In pre-processing stage also, in nowadays people are using machine learning, and in final classification stage also, people are using your machine learning techniques. Now, before going to your main artifact slides, we should have basic fundamental knowledge of your wireless communication standard for your transferring your data from your wearable devices to your different your gateways or your routers. It may be routers. So those are Zigbee technology we are using, Bluetooth, also IRDA, MICA, 802.11g. These are the communication technology which are being used for transferring data from wearables or sensors to nearby your nearby access point, nearby your gateways, and such that we can send the data to cloud. Now, let us move to frequency band, power consumption, data rate, everything is mentioned. If your signal is 2D nature, if your signal is 2D in nature, it is obvious you need your better data rate to serve the purpose. And here, since in EEG, it is 1D time series data, one-dimensional time series data, so you can easily send with less data rate with respect to your image data. Now, these are some device by which you can extract your some important your physiological parameters, oxygen saturation meters, electrocardiogram monitor. These are your again repetition of your these things. You see your here ECG sensors or EEG sensors you can take, next followed by your IoT cloud, and finally you are getting the recommendation across your mobile app. Now these are again some functional block diagram, repetition of your earlier theme in block form. So here we have to focus on data processing part. In place of filtering and feature extraction, we can use machine learning here. We can replace these two blocks with machine learning. Now, its utility, you see, data visualization can be done. And finally, your recommendation. Now, these are some example of your some sensors, wearables, where sensors are implemented in this watch, which can capture your oxygen saturation, heart rate, activity, and temperature. So these are some example of your wearable implantable medical devices. You see, across brain, you have deep brain neurostimulator that is being implanted, and by capturing this data, you can have better your diagnosis capability. Afterwards, if you look into next slide, nowadays electronics has skin electronics. There's a huge advancement in skin electronics, and here sensors are placed on screen instead of your wearables. So this new era of your skin's electronics is you're coming up. By implanting your different sensors on skin, your different polymer based your substrates are there, which can capture your temperature, your blood saturation, those values. Like this way, it is being implemented. So this is your background. You see in whole body, in which location, how sensors can be, what type of sensors can be implanted. Uh, Though you see, it can comes in terms of your ring, watch, wristband, armband, on t-shirt also, clothes also, some sensors can be placed, necklace, on head, on the different part of your helmet, you can put your EEG sensor and get the data continuously. Suppose for several hours, for 10 days, for 15 days, you can take the data, time series data, and do analysis for diagnosis. So these things afterwards, this is your background. Whatever we have discussed during this your half an hour time, that is your background of this problem. Now we'll look into your EEG artifact, your removal framework for healthcare application. That part we'll look into. EEG artifact removal framework for healthcare application. That part we'll look into. So you see, what happens? This is your background one. This particular diagram in figure 1 shows how different EEG sensors are placed on our head, scalp. So different electrodes having different nomenclature. You see, if you look into this diagram, C means some central location, C3, CZ, C4, C, and this side you see T4, T6, T3, T5. This outer layer you have T, and back side you have O. This way, and in front panel, front part, frontal lobe, you have FP1, FP2, FP3, FP4. So those things are there. So EEG sensors, it's having your different your configurations. So it is, if you look into 10-20 arrangement, it is called 10-20 standard your EEG arrangement. In that, you see, you have several sensors placed on your head, and location is your feet, fix. Suppose due to eye blinking, some fluctuations occur on EEG, it will come up in some channels, not all the channels of your EEG. Suppose if you move your hand to this muscular artifact, this is called muscular artifact. So that artifact would be reflected in particular some channels. So no, it would not reflect in all the channels. So that's why which channel you will take for your study, it depends on what kind of problem or what kind of disease you are going to diagnose, or what kind of problem, what kind of artifact you are going to remove. So based on that, we take the channels. We don't take all 21 channels always. We take a few channels for our study, and if it is required, things are critical, then in first page we analyze all the channels, and afterwards we go for your selective specific channel for our study. So you see one important statement is written over here. It measures voltage fluctuation resulting from ionic current within the neurons of the brain. Neurons of the brain. And afterwards, you see EEG signals are measured from electrodes position on the skull. It is mentioned. So we should have basic idea about this. And afterwards, background to EEG rhythms. EEG rhythms. In EEG, what are the important your signal components? It is well defined. Those are your delta waves, theta waves, alpha wave, beta waves, and your gamma waves. You see, each and every frequency bands are well defined over here. Different frequency bands are well defined here. Delta represents your very low frequency, less than 4 Hz. Theta is between 4 to 8. If you look into diagram, you see your delta means less than here, this block, this highlighted block, less than 4. Theta means between 4 to 8 Hz. It lies within your 4 to 8. Alpha wave comes under 8 to 13, and your beta wave is between 14 to 30, and gamma wave is your greater than 30. It is wide range. So most of the signal lies within the your say 50 Hz, and some of the gamma part may comes within the range of you some a few kilohertz sometimes, but our main focus would be low frequency part. So these are the why we have divided this part, your delta, theta, alpha, beta, gamma. You see, for a particular activity of brain, this kind of waves, it generates this kind of waves. So if you capture those, if we capture or we can identify this kind of waves is generating in a particular time instant, so we can say a particular person is doing what kind of activities. Like alpha wave, its frequency band is your 8 to 13 Hz. It generates during relaxation mode. In the same way, when people are very focused, like suppose we are listening the lecture, we are very much focused, highly alert, and we are doing active thinking. This time our brain is generating beta waves, and its frequency band lies within 14 to 30. So suppose using your EEG, your sensors, if you capture our brain signal and analyze, so during this particular time instant of time, we can observe some beta patterns are there. Beta patterns are there. So you see, it is well defined. When your drowsiness in adults or teens are there, or deep meditation state, in that theta waves are there. It lies within 4 to 8. When people are in sleep state or dreamless sleep states, in that your frequency, if you capture the signal and find the frequency, it lies between less than 4 Hz. That time the brain is not so active. Suppose anything mishappening are there, like due to some seizure activities, so you see left side diagram, here lot of fluctuations are there. This is your normal one, EEG, one channel data, seizure free, and second one is your with some fluctuations. Means something happened. It may be some neurological disturbance, or it may be artifact. By viewing this waveform, we can't decide whether this is artifact or it is your somewhat any neurological problems occurred, something unusual thing occurred. So it is very vital to first pass the signal through one filter, and afterwards if you see still fluctuations are there, so from that we can say the patient needs some your care or treatment. Now here challenge is that during filtering some important medical information may be removed. So challenge would be how to preserve your real your brain signal and remove only artifacts part. So now one important thing is that during what would be the sampling frequency? What would be the sampling frequency of this your signal? This is common question to the audience. Say if our signal lies within this 50 Hz band, say 50 Hz band, so what would be the sampling frequency of this signal? Suppose this is your continuous in nature, we want to sample it, and then we'll analyze, store this in computers and analyze for further processing. So what would be the sampling time, minimum sampling time? What would be the any person can answer for interaction purpose? Otherwise, it becomes very boring or monotonous. 50 Hz is your sampling, your 0.05 Hz to 50 Hz is your important information. It lies within that band. Important information of EEG signal lies within 0.05 Hz to 50 Hz. So, what would be the sampling frequency such that we can reconstruct the signal also? Suppose we want to transmit this signal from one end to another end to IoT network. What would be the sampling frequency? Simply, we have to use your Nyquist rate. 2 times of your maximum frequency present in the signal, that is your 50 Hz. So it would be 100 Hz, and we keep SEPA side. So in the literature, if you look into, it would be around more than 200 kilohertz. People are keeping 200 Hz to a few kilohertz. So this is the thing regarding your sampling. Afterwards, your next background of EEG artifacts, we need to know those are what are the different artifacts are there. 2 types are there. One is your original, and second is your internal, and second is your external. Internal are biological to the human being, and non-biological are your external. So among your internal, one important artifact is your ocular artifact. Second is your muscular artifact. Third is your cardiac artifact. Muscular means some noise arises in the EEG signal due to muscle movement, hand movement, or hand muscle movement, or leg muscle movement, that kind of thing. Cardiac artifact means we have heart is pumping blood. So due to that, it generates your ECG signal, and this ECG signal interferes with your EEG, means on brain. EEG, some traces of ECG would be there in EEG, brain signal. So that artifact is called cardiac artifact. Next, your sweat artifact. Due to sweating also on head, some artifacts your produces. And last one, glossokinetic artifact. This is also due to your different type of movement, like you say eye movement. No, sorry, chewing. You are chewing bubble gum, suppose say. So it would have it would be some artifact would be there in brain signal. So that kind of thing comes under that. And external artifacts is your instrumental artifact, interference related artifact, interference with other signals, or motion artifact. Suppose you are recording the data for 10 days or 15 days through some wearables, and patient is not in fixed setup like hospital setup. He is moving and continuously data is being captured and stored across your cloud. So that time motion artifacts also arises. We need to take care of that motion artifact before analysis. Next, you see first figure, one plot is there. In that, the red encircle part is your some artifact present in EEG data. That is your biological artifact. It is mentioned. Some sudden fluctuations occurred in EEG signal, and here some your non-biological artifacts, some peaks there in regular interval due to say emotion. So here it is some definitions has been given in the slide. So from this slide we can have some minimum information about artifact, what are the different artifacts, different types, and its source, which introduce in brain signals. Now let us move to next slide. Ocular artifact are most common and influential artifact often dominate over other biological contamination sources as well as non-biological interference contaminated sources. You see, OA means ocular artifacts is combination of eye movement, blinking, eye fluttering, eyelid movement, slow eye movement. So many things are there. If you combine those, which is called your ocular artifact. Now, ocular artifacts significantly distort EEG recordings, and consequently, the presence of OA needs to be accounted for in any EEG study. Here, in this your session, we'll devise methods for successful removal of your ocular artifacts from EEG recordings, though it's having you major challenges. We are looking forward for developing certain methodologies for removing ocular artifacts from EEG. It is essential and important for interpreting EEG properly. Now let us look into this pictorial view. If you look into this pictorial view, this red mark portion shows some fluctuations in all the channels. It starts with your T1 channels to AP2 channels. In all the brainwave channels, brainwave signal having some fluctuations across this. That particular time interval of your 8 seconds, around 8 seconds. Now, that is due to eye closure. When we close the eye, that time it interferes the brain signal, a smooth brain signal, and you see it is highly you'll find your high impact on FP2 and FP1 channels. In other channels, your effects are quite less, but in these two particular frontal lobe channels, FP1 and FP2, your sensors, data, you'll find your fluctuations. So in earlier we discussed कि for any particular application, you need not to consider all the channels. You have to process the specific channel as per your application or your diagnosis requirement. When your things are unknown, that time we need to analyze all the channels in first page, and afterwards we need to your specifically analyze some of the channels. Now, before going to this, let us take your just 1 minute break, since we have delivered around your near about 40-45 minutes. So a small break for 1 minute, then we'll again proceed further.
Sorry to interrupt you, sir.
Yes,
Your
yes.
voice is not coming clear, sir.
Voice is not coming properly.
Yes, sir. Yes, sir.
Now it is coming.
Yes, sir. Yes, sir. Thank you. Thank you.
So if you face any inconvenience, yeah, you need to just let me know so that
Yes, sir.
I
Sure.
can
Sure, sure.
transition. Now let us continue. Artifact your removal methods. We'll discuss about some artifact removal methods. So these methods are very much vital and useful for other 1D your noise removal cases also. Suppose if you look into your ECG signal, electro cardiogram signal, that is also 1D signal. So in that case also, we can use your this kind of your techniques, statistical or adaptive or machine learning based techniques. So let us give me some examples which can give you a basic your background. Now, first thing is your EEG artifact handling. So, first method is your we are using BSS method. BSS means blind source separation method. Blind source separation method. This method is very much popular if you look into literature of EEG artifact removal, and this is the state of the art method. It having your three part. One is your, suppose you have some unknown source. Unknown source means you have say 21 channel. If you take one channel of EEG as a say unknown source, so from that you can find your mixing matrix. You have to multiply mixing matrix with your unknown source. So you'll get your AS, A into S, and afterwards, suppose if any white noise is introduced or any kind of artifact is introduced, so it is added, and afterwards you have observed signal. X is called your observed signal, and next block is your identification block. In that block, one important matrix is there, that is your unmixing matrix. First one is called your mixing matrix. Second block is called just inverse is unmixing matrix W. And by your if you multiply unmixing matrix with your X observed signal, you can estimate the source S. Estimate the source S. So through this process, you can your denoise EEG signal. For better understanding of this particular old method, your state of the art method, you can refer different articles available in the literature. Simply you have to Google BSS, you'll find lot of your literature, and it is performance of BSS method is also very good for estimation of source. Now different other techniques are also your very much your useful, like your ICA, CCA, PCA, and MCA. So these are well known your techniques by which you can also remove the your EEG signals, like your principal component PCA, independent component analysis are there. So many your state of the old techniques are there. So for devising new technique, you need to compare with your state of the art techniques. So those are the techniques available in literature. You can refer literature for better understanding of those your techniques, because we have time limitation, so we can't go through each and every old techniques. Now you see in this technique your manual intervention is required, and these are not automatic, these are semi-automatic techniques. Here sometimes you need to your manually tune different thresholds and parameters. It is not automatic in nature, so it can't be deployed in your wearables or where things are automatic, need your automatic solution, fast solution. Next method is your filtering method. In filtering method, you see it is better in performance, but it needs your training. If you know the basic principle of your adaptive filters, you need to train the filter also, such that it can adapt the correct filter coefficient to denoise the signal. Suppose without your update or training, you can't deploy adaptive filter for long time. Suppose one particular filter is on operation, so it need your regular your regular training or updates after certain interval such that it can work properly. Why it is so? Because if your outside environment change, your filter need to adapt as per its requirement. You see here also you have primary. If you look into adaptive filter diagram, you have primary signal. It's having your artifacts in EEG in certain your channel. It is added with your signal. It becomes your SN, and you have some reference signal, reference EEG signal, and it is passed through your this thing adaptive filter, and error is calculated, and that error is your feedback to your adaptive filter coefficients, and your filter coefficients your update based on your requirement. And EOG, what is EOG? EOG is nothing but your eye movement related signal, eye lead movement related your signal. So here drawback of this channel technique is that filtering technique is that you need one reference channel. You need one reference signal to process this your data. Now, time series analysis. For time series analysis, apart from your adaptive filters, in literature you will find your wavelet based denoising technique very suitable for EEG. Here, a lot of permutation and combination can be done, and authors has done, and lot of scopes are there for further your permutation and combination. So here, if you look into, you can change the choice of threshold. You can change the mother, select different mother wavelet. You can vary the decomposition level based on your requirement and come up with some new solutions. So what are the basic block diagram of this kind of your wavelet based denoising? You have contaminated EEG input signal followed by wavelet based signal decomposition. You have wavelet tool available with your MATLAB, or different Python libraries are available. So you can use any library or any tool for this kind of decomposition, or you can write your own code. It is available in a lot of web resources are available for existing algorithms. You can download and play with these algorithms to have a better solution. Afterwards, you have automatic or manual artifact elimination. That is our motto. We do that by putting some threshold in wavelet. What we do, we decompose your artifact added signal into different your pass through different high frequency and low frequency, high pass and low pass filters, and afterwards we segregate the noise part by putting some threshold, and we reconstruct the signal. So by applying inverse wavelet, we are reconstructing the signal, and it would be your noise free. So what is the process? Decomposition in several levels, and afterwards you have to put some threshold to remove the noise, and afterwards you have to reconstruct the coefficients to get your artifact free EEG signal. So here also choice of threshold, selection of mother wavelet, selection of decomposition level, it varies with the signal pattern. So it is also not you're very much automatic in nature. Manual intervention is required. So you can't install this kind of wavelet based denoising technique for your in your uh, smart devices like your IoT based wearable devices. Now empirical techniques are also there. It is complex, computational complexity is your high, but it gives your better accuracy. EMD, EEMD, these things you know, like your empirical mode decomposition. So here in EMD or EEMD, whatever variants are there, what do you do in that? Like wavelet also, here we decompose, but we decompose in IMF function. IMF, your functions, different IMF functions, and afterwards, what do you do? You see, you have contaminated EEG input signal, followed by empirical mode signal decomposition, and afterwards, we decompose these things in different IMFs. Afterwards, we set some threshold based on some statistics, and afterwards we again apply inverse empirical mode signal reconstruction, and through here before reconstructing we remove undesired IMFs, intrinsic mode functions, which are responsible for your noise part, and we reconstruct the signal. So this is your again some manual intervention is required. These are good techniques if you process the data across cloud. After getting the data across cloud, and afterwards if you process these things offline, it's fine. But in real time, some again your problems are there. Afterwards, if you look into some literature, here you see you have experimental control, time domain and frequency domain regression techniques, adaptive filtering techniques. These techniques deployed for different schizophrenia kind of disease, for detection of your schizophrenia kind of disease or epilepsy kind of disease from disease. We use your adaptive filter, time domain, frequency domain regression, different several techniques for artifact your removal. In the same way, some literatures are available like your principal component analysis, but it fails when signal are comparable amplitude. Method needs more prior information. These are the limitation. MCA, morphological component analysis. These are you see published in 1719 old papers are there. It needs morphological decomposition component to describe the signal. So you have ICA, independent component analysis, also published in several years from 2000 to 2019 with different variations for detecting your epilepsy. And you see your computational complexity is your more, execution time is your more. So its efficacy is good, but computation time is your more due to more complexity. So these are the some problems are there. Now you see wavelet transform methods start published in 2006 to 18 for removal of your this kind of artifacts, and some limitations are also there, like your selection of mother wavelet. Already we have discussed these things, setting of threshold, Here you see empirical mode decomposition based ocular removal algorithms also published in your 2021 even. These are recent starting from 12 to 21 literature available for analyzing the sleep pattern. It is available. So here, what is the limitation in EMD? EMD method has limitation of mode mixing, lack of theoretical background means uh, these are there, and here processing time is also high. Now we'll look into non-biological artifact in EEG or motion artifacts. Motion artifacts can occur from different sources like ground reactions, force, cyclic motion, head movement, which are related to daily activities during ambulatory EEG recording. So this is your motion artifact. Nowadays, some papers are coming up or published in motion artifacts, but scopes are there. Research scopes are there. The intensity and type of movements can vary person to person, make it most versatile artifacts. Now, what are the challenges due to these artifacts? It misleads in detection of prominent pattern present in EEG signal. It deteriorates the brain-computer interface performance during practical applications. Several BCI application has been devised. Nowadays, some research going on, like suppose a driver is driving the car, during driving whether that particular driver having sleep tendency or not, using BCI by putting some electrode on EEG electrode on scalp through a two channel, it can capture the data and it can detect whether sleep related wave has been generated or not, and based on that some alarm can be generated. So these artifacts, motion related artifact, can interfere the result. So removal of motion artifact is very much important. So here we have listed head movement, hand movement, body movement, jaw movement, walking, running, sleeping, talking, working on PC, watching TV, and many more things into this category, motion artifact, your category. Actually, we have to understand the problem in depth, then only you can devise solution. Several solutions may come into your mind, but understanding of problem is very much essential for giving the solutions. Since you people are working in the area of your machine learning, you are exposed to those your tools, and lot of tools are available. Uh, your tools are available, so you can apply tools for this method. Now, you see, I think it is 1 hour over. We will take 1 minute break and next continue because it would be monotonous. 1 minute break, then again we'll continue. Before concluding this artifact part, if any faculty member having any your question, so we can take that question and we can, after that we can proceed. Within this 1 hour time, we have discussed about motivation of this topic and your background, what are the different artifacts are there, some of the state of the art techniques which can be employed for removal of your artifacts from EEG signal, and some applications where you can these particular EEG noise free signals can be used for the purpose. So if anybody having any question, any concern, so you can share. Otherwise, we'll move to your next your slide. This slide will discuss I will summarize the matter. Will summarize the artifact removal techniques using these block diagrams. Okay. So let us again summarize this. If you look into left block, here different EEG sensors fitted with fitted for capturing the data, EEG data. Now different artifacts are added with during recording process. So nature of artifacts may be biological or non-biological in nature. Under biological, you have ocular artifact, muscular artifact, cardiac artifact, sweat artifacts, and it may be glossokinetic artifact. And afterwards, you have non-biological artifacts, another category. So in this category, you have motion artifact, you have interference related artifact, you have instrumental artifact, and some volume conduction or supervision artifact is also there. You can go through literature in depth if it is required. Afterwards, processing part, signal pre-processing. In signal pre-processing, what we are doing, we are removing the artifacts using homogeneous method. Simplest method is your regression method, but it does not work well. Followed by filtering method, followed by your wavelet method, followed by blind source separation BSS method, and other techniques like ICA, PCA, CCA, and MCA. We have discussed these things during literature review part, and afterwards your EMD. Or it may be hybrid. You can combine. To this part is very important, hybrid method. Nowadays, whatever papers are coming up, those are based on your hybrid method. You can combine BSS with WT, like you have considered 2-channel data or single channel data for removal of artifact. First go through, just pass your signal through BSS, blind source separation, and afterwards you apply wavelet transform. And with this hybrid technique, you can have one solution. Another solution may be BSS plus EMD. Third solution may be BSS with AF. In the same way, you can have BSS with machine learning or other deep learning or CNN based method. So you can try different iteration, permutation combination with some logic. Without logic, you can't put this, because blind source separation is very much essential, followed by some decomposition technique, or you can use some blind source separation technique followed by machine learning. So in first step, suppose you are not able to eliminate the whole part, using another technique with the help of hybrid combination, you can have your better results. It may be. Now, after getting the new result, you need to evaluate the performance. So, how to evaluate the performance of your techniques? For that, three type of evaluation parameters we use, categories of evaluation parameters we use. Those are signal power related evaluation, error related evaluation, and signal information related evaluation. Signal power related evaluations are like signal to artifact ratio, peak signal to noise ratio, difference in SNR, power spectral density, distortion. Error related like mean square error, we calculate root mean square error, we can calculate normalized mean square error, we can calculate mean absolute error, we can calculate, or relative error, we can calculate. So these things we have seen in different literature. So from that we have combined these things. And the last one is your signal information related evaluation. Correlation coefficient, mutual information coherence, these things you can calculate for this. Now, afterwards you are getting your clean EEG signal by removing the artifact, and it can be applied for clinical diagnosis or brain computer interface applications or application specific feedback purpose. Now, research gap. Our main purpose of this lecture is to highlight some research gap where your researcher or faculty members can work if they have interest in this or working in this domain. So here we have just given a gist where we can work, like your it is not possible, this last line is given, it is not possible to remove simply by filtering all kind of artifact. Remove simply by filtering, as frequency range of recorded neural data can be from some in the range of hertz to some, it may be kilohertz if it is gamma wave. So you have to devise a technique which can take care of all the artifacts. That is main challenge, research challenge. Papers are available with your, say, in some cases motion artifacts it can remove properly. In some cases it may be ocular artifact remove nicely, but if you combine your 3 or 4 kind of artifacts, or your signal, recorded signal is your contaminated with your multiple artifacts, in that scenario many techniques your fails. So that is your real research challenge. So researchers, faculty member can address this challenge for their future work, and they can work in this domain. Here you see some pictorial view has been given to motivate you. Before artifact removal, some spikes are there for chewing. This is due to chewing artifact. Chewing, suppose bubble gum. Spikes are there. By applying artifact removal technique, you can filter out and you are getting your smooth, your blue color, your waveform. I be blinking at artifact in this window, it is reflected, but after a red color spikes. But afterwards, by applying your techniques, you can remove and it becomes being smooth. But challenge is that when multiple things are available, whether your algorithm can detect those things and remove properly. That is your main challenge, and we have to work in that objective. So objective of research would be motion artifact suppression from EEG signal using a hybrid signal processing approach. Motion artifact is your very prominent artifact in a long time your recording of EEG. Ocular artifact suppression is also very much important because it is quite frequent, and multiple artifact also very much important. So here we can use your machine learning method for removing those artifacts. Now EEG data set, you need some EEG data set. Suppose if you are new in this field and you want to explore some EEG data, from where you can get this. For this getting the EEG data set, this slide is very much vital slide. So you take a snapshot of this slide and you can explore, like your Temple University artifact corpus is there under ocular artifact data set. This is very your large data set. It's having your variety of your information, your databases, very large. If you request them for research purpose, you need to use this database, so they will give permission and you can access the database. And other databases are also freely available. Some database are paid, but ample amount of data are available for carry out the research in this domain. Next, one of my PhD students has done this work. I am going to present that most recent work he has done. One algorithm has been designed for removing the motion artifact from EEG signal. So here you have combination of your EMD with your LOG filter. LOG means Laplacian of Gaussian filter. So we have modified existing your LOG filter, and we have modified EMD also, empirical mode decomposition, your technique. And by combining this modified existing technique, it becomes some hybrid technique, and that hybrid technique is being employed for removal of motion artifact. And we have seen it shows promising result or comparable result with existing state-of-the-art techniques. So suppose start with your noisy EEG signal. This is nothing but some time series data, sample data. We need to, when we'll download the signal, that time we need to know the sampling frequency of the signal also. You need to note down the sampling frequency of the signal, whatever uploaded in the database during capturing of that signal. It is very much vital data. So it is say 256 hertz or something like that, or a few kilohertz it may be. So suppose you have very lengthy 1 day data. For analysis purpose, we divide that lengthy data into some small windows. Say if you take 400 samples in a single window and process next 400 samples, that way if you divide your lengthy signal into several your non-overlapping windows and process window wise, so then that way we process the thing, and afterwards we apply EMD, we decompose the noisy signal using empirical mode decomposition, and we decompose these signal into IMF functions. You see I equal to 1 to k number of IMF functions. Now these IMF functions are of two category, low and high. We'll divide, suppose we have taken k IMF functions, so among k we have taken high frequency up to k by 2 in one part and remaining k by 2 plus 1 in another part. So that is related to your motion artifact dominated low frequency component. And afterwards, what we are doing, we are combining all low frequency IMFs, and we are passing through modified Laplacian of Gaussian filter. And here we have applied some optimization technique for selecting the LOG filter parameters like your coefficients. And afterwards what we have done, after filtering, we got noise free low frequency part. After passing your LOG, passing the signal, low frequency component signal through the LOG, modified LOG's filter, we got your almost noise free your signal. Now we have added, this is XLN is your almost noise free low frequency part, and you have high frequency part IMFs. Now we have combined these two and we got denoised EEG signal varying from n equal to 1 to n. Now we'll compare with reference signal. Here also there is the requirement of reference signal, reference EEG signal, and we'll calculate the evaluation parameter whether that whatever denoising we have done that is correct or not by applying your RRMEC or MEC means by error those parameters PSNR, and this tuning will carry on. This is your feedback system. So this is your noisy EEG and this is your denoised EEG. If you look into performance evaluation block, one input is your noisy EEG and another is your noise free EEG, and we'll find the error of the signal, whether error is low or high, and we'll compare with different existing technique whether our technique, proposed technique is your useful or not. So you see, using different your combinations, you can devise very beautiful algorithms, which can solve our purpose. Now you see data collection and pre-processing part. In that part, the left side different, it shows different electrodes, and afterwards you have your noise channel and reference channel. One channel is your reference channel. We have to keep one reference channel, and this is your any channel like your FP1 channel we have taken. In front part, we are extracting some your 400 length data, say that is your, or 1 minute data. It depends on your sampling frequency, how many samples would be there in 1 minute data, 1 minute epoch. Then we are doing some baseline corrections and amplitude normalization. Afterwards, whatever signal we are getting, we are doing your pre-processing part. Here in right side, it shows your different activities of your motion. When you are standing, you are walking, you're walking and doing some brain computer interface kind of your work. Next you're standing again. So accordingly you see what is the fluctuation. Some fluctuations are there during standing also, because it is very difficult to stand still. During walking, fluctuations are more, and during walking plus other brain activity, fluctuations are very dense. So you have noisy channels of whatever channel you need for your application. You have captured those data, multiple channels, extracted 1 minute your window, done baseline correction, amplitude your normalization, and you through different channel you can see key different activities has been reflected. So you can adapt any data sets as per your requirement, and you can plot those. You can apply different algorithms for solving your purpose. Now whatever method has been proposed, modified EMD and LOG filter, this is your pictorial view how EMD is working. We have decomposed artifact based EEG, your one channel data, now number of samples here it is mentioned 15 10 to the 4, and you see we have decomposed these things into some intrinsic mode functions, IMFs, IMF 1 2 3 4 up to 10, IMF 10. Beyond that you can't, if you break it, you will not get any information. So you have to limit. So out of these 10, some IMF contains your high frequency and some IMF contains your low frequency information. So the 50% IMF which contains your low frequency, will identify those and will pass through LOG filter and will remove remaining low frequency noise and will combine that filtered combined IMF with the high frequency IMFs and will reconstruct the signal. So you see here noisy EEG in red, reference EEG in blue, and denoise EEG is achieved in terms of your say black. This is your we have processed this in real time now through simulations. Now now your denoise signal spectrum. If you look into spectrum, it look like this. And if you look into pulse spectral density plot, pulse spectrum also versus frequency, it look like this. Noise EEG reference and denoise EEG, its pattern. This is your main lobe and these are side lobes. So you see here what is the innovation in this technique. Innovation is introduction of LOG, and when we should your stop this breaking, how much this IMF function will take, that we have decided that is your automatic. Earlier it was manual. Now we automated this by applying one objective function. Now this is your output of modified EMD and LOG algorithm. Here noisy ECG is red and filter EEG through this method is your black. So during standing, walking, and walking plus BCI work, this kind of variations we have seen. This is your denoise signal spectrum we have shown, and PSD plot also we have shown. PSD plot also we have your shown. Now from PhD plot we can see key noise power, what is the signal power, noise power, those statistics we can see. From your spectrogram we can see the time frequency, your localization of the signal, time frequency, your domain. Amplitude is your time domain, next your time frequency domain, and third domain is your frequency domain. In all three domain, time frequency and time frequency, and both time frequency scale or domain, we have analyzed the your signals. Now this slide is very important. This is related to performance evaluation. What kind of performance we got, we can evaluate using these parameters we have discussed. It is again defined, well defined. Those are xn is your reference signal, dash n is your reconstructed signal, yn is your artifactual signal, e1n is your error between x and y is your artifactual signal, and x is your reference signal. So that difference is called E1n. En is your error between x and x dash. X dash means reconstructed signal, x means reference signal. R-ref means autocorrelation of reference signal. REC means cross correlation between reference and reconstructed signal. RART is cross correlation between reference and artifactual signal. And TART means time duration of artifact. TART means time duration of artifacts. So we have to detect first the artifact, and next we have to pre-process. So instead of taking all the windows, we have to detect the artifacts, and we will take the window surrounding that artifact, and we'll process the thing. T total means total data length. Now you see these are some relations by which we can do the measurement, distortion measurement. It may be spectral distortion, it may be your SNR related your measurements. So programs are available in web resources. So for 1D signal, your performance evaluation, artifact removal performance evaluation, we use this kind of techniques. Now this is your whole process of ocular artifact suppression from EEG. You have to pre-process it, and next you have to measure the performance of your algorithm. Now conclusion of this particular work, EEG signal is susceptible to distinctive biological or environmental artifacts. Artifact correlation is one of the severe problems encountered in biomedical signal processing. In recent studies, researchers are more devoted to consolidating various existing traditional algorithms to make hybrid techniques rather than putting their efforts to modify the conventional methods. Here, we have successfully proposed and implemented modified DMD and optimized LOG filters for suppressing the motion artifact from EEG signal. The obtained experimental values of the performance matrix revealed that the proposed algorithm outperformed the existing state-of-the-art EEG signal. I have not given the performance parameters, graphs, and those things because due to shortage of time. Main thing is key, if you apply those your formulas, You can evaluate the performance and plot, but main thing is with the algorithm. Main beauty is your algorithm. How to develop your any new algorithm, that thinking should be developed. Other things are your these are the reference used in this work. Now, any question from audience side regarding this work? And afterwards, we'll move to next work, that is denoising of EEG using machine learning. Since your last one is your hybrid method for artifact removal, and this technique, last one is your denoising of EEG signal using machine learning technique. We will cover last part, your denoising of EEG signal using machine learning techniques. So I'll take your small break, a small break for the same. Take 2 minutes break, then again we'll start this. Let us now let us start again. Your next problem, we have how much time? We have 15 minutes time. We'll quickly review your next case study. That is your removal of your artifacts using your machine learning technique, identification and also removal. So if you look into this block diagram, you have EEG data recording in across input. Next, you have feature extraction part, followed by one machine learning part, like your support vector machine we have used in this. And our purpose is to detect the eye movement, that means ocular artifact, and also remove that artifact. Now, what you have to do for this? You have to train your SBM. You know SBM work well for two class of signal. One is your noise free, and second is your having some artifact. So after identification, you have to pass this through ICA decomposition, uh, independent component analysis, ICA decomposition, and followed by your multi-resolution analysis like your DWT, and afterwards you are using inverse ICA, and through that you are getting your artifact free signal. So you see here in this technique, machine learning is being used for identification purpose, whether that signal having artifact or not. And for denoising purpose, ICA and DWT combination has been used. Now these are basics, no need to review. These are already covered. You see how it look like multiple channel EEG. Now these things already we have discussed. About database, it is mentioned 29 subjects are there, and here also you see different mathematical descriptions are there for finding the features from EEG signal. ICA decomposition details has been given for multiple EEG. So here kurtosis, MMSC can be used for feature identification of artifacts. So in some of the work, like your blinking, eye blinking can be identified based on these features, like your say kurtosis, MMSC. Now wavelet may be different type. It may be orthogonal, it may be Morlet, different. It may be your different discrete. Obviously, it is discrete wavelet. We have to use discrete wavelet transform. Now reconstruction also just reverse process. This is your some 14 channel EEG having some artifact marked as your red ocular artifact. Next your here it is eye movement related some fluctuations are there. It is available near about 4.5 millisecond. These are all other eye movement related fluctuation in other channels. These are the kurtosis and MMC parameter, independent component your parameters from different ICs. We have calculated kurtosis parameter and we have plotted. It can be used as a feature. So you see channel wise it is given 1 to 14. Using earlier proposed method, it has shown some statistics. Using unsupervised approach, some statistics, some performance measure they have shown. So we would skip these things because one important thing is there we need to cover: noise removal of EEG signal. Removal of EEG signal using machine learning. So this is very important block. If you look into this important block, first part is your signal lengthy time series data. We are dividing that lengthy time series data into some sub blocks, and here in this particular work, 1D your CNN has been used. 1D CNN has been used, and here number of layers is your M. In generalized form, you see multiple layers are there. So if you take M equal to 3, so it's having your 3 layers, and in each layers you have n number of filters. N number of you have m number of your layers, convolutional layers, and n number of capital N number of filters in each layer. So here in CNN model, you need to tune the number of filters as per your requirement and number of layers. Vertically you can extend, horizontally you can vertically you can extend, horizontally you can extend. Some literatures are there where authors have extended is vertically, some in horizontally, and some both the combination of these things. And in last part you see one objective function has been defined which restrict the error, means when error is less, that kind of features it is taking. Here in CNN network, no other feature extraction, your feature separately features are not you are extracted for training purpose. Different combinational layers extract the features, and with their different combinations you get the final feature, and that feature is your being trained to the network. And one nonlinear relationship is being established between input and output. Between input and output. So here, with this proposed your architecture, you'll find your denoised EEG signal, clean EEG signal after your completion of your certain iterations. So here you see it is mentioned in this paper they propose your CNN model after convolution operation. The size of the input is reduced, and the adding input to it, leave it. Now we'll move to your this part. This is your detail, your structure, architecture of your this CNN network. Here if you look into, you have three residual block 1, 2 and 3, and if you look into conv 1D, here 32 filters are there. This last number is your number of filters. It denotes your number of filters. And if you look into what is BN, BN is your batch normalized layer. Batch normalized layer is called your BN layer. And you have your ReLU layer over here. So this kind of combinations has been used. First 32 filter followed by 16, next 32. And different type of your series combination has been done. You see the different type of series. Here it is parallel and here it is series. Different type of combination has been done. And so ultimately after passing through this structure, you are getting your noise free signal. And here if you look into your different kernels, these are the kernels. CONV 1D having 1 into 5 kernel and 32 filters. Residual block 1 having 1 into 3. Residual block 2 having 1 into 5. That way, for each and every block wise, things has been, kernel configuration has been, and filter configuration has been defined. And if you look into these things in more simplified way, you have this kind of three layers, and it is one-dimensional residual CNN denoising model. It uses 1 is cross 3, 1 cross 5, and 1 cross 7 convolution kernels of different scales to extend frames of different size and orientation. Now, if you look into this block diagram, how denoising is happening, you have two page. One is your training page and another is your testing page. in training page, clean EEG signal samples are there, and here you see some noisy EEG training samples are also there. We have to introduce one objective function, and we have to take the extract the features with the help of convolutional different layers, and afterwards it passes through your training page, and afterwards testing page, noisy EEG is taken, next feature is extracted, and again through this previous training, it is extracting the noise from the signal, and you are getting your clean EEG. Now, if you look into several window, we have divided lengthy signal into several windows, and in several window, your fluctuations pattern would be different if you look into, and after cleaning, you will get your clean output. This is your algorithm. It is being used in this particular problem. Artifact removal by using the proposed 1D RES CNN. Here, the sliding window method is used for segmentation of your time series signal, followed by normalize the noisy EEG. Next, the construction of a one-dimensional combinational neural network. Next, your network model training process is being done, and afterwards your normalization operation is done with the help of your equation number 4, and afterwards your reconstruction is done. Here objective function has been defined, equation number 6. The loss function of this paper, this particular work, uses the traditional mean square error method to train 1D CNN by a small batch gradient descent method, and minimize the loss function by Adam optimization method, where n is the number of training sample and number of sample per training. That is number of sample per training. Sample means EEG samples. Loss function can be used to learn the trainable parameter. So you see, this is your signal. After DNN method, we got your this red one EEG signal added with ECG noise. After your CNN applying 1D CNN method, we got your relatively less noisy signal. And if you look into a spectrum, you will see the improvements are there. And here for if you have EMG artifact, so after removing the artifact, red signal is achieved. This is your DNN result for EMG artifact. This is your EOG, eye movement artifacts has been removed using DNN and 1D CNN respectively. And these are some other your compared with other state-of-the-art technique with your proposed and DNN technique, and it is observed that a proposed technique gives your better result. For EMG noise, this is for EOG signal, same thing. For all kind of artifacts is getting better performance. Here also it is being compared with in different SNR level, and a proposed technique giving you a better result. If you look into here also, you see for EMG, for ECG, better result is giving with respect to other your techniques. Here also you see correlation parameters also being calculated. We have calculated. Now conclusion, CNN has better local feature expression ability and can better utilize the correlation between EEG signal and noise signal. And EEG denoising method based on deep one-dimension residual convolutional neural network is proposed. The deep convolution neural network is used to establish a regression model to express the complex nonlinear relationship between noisy EEG signal and pure EEG signal. This is a very vital point. And convolutional neural network filter residual data, use large data sets to improve signal denoising and help capture the main feature of EEG signal. Means if you increase the training data, it will give you a better result. Through this, it achieves a small RMSE and better signal to noise ratio on the test sets, and has better noise suppression ability than other denoising method. Actually, due to time limitation, we have covered this part very fast. So you can refer your research paper for this for better understanding. A lot of literatures are coming up in this domain. With this, I would like to end today's session. And now, if any faculty member having any questions, so we can.
Participants are requested to any query if you have. Please raise your hands. I think no questions. So thank you, sir. I would like to express my sincere thanks to Dr. Bikash Chandra, sir. To
Thanks.
wearable IoT, sensing architecture, wireless communication standards for WHM, biological artifact removal methods. I also wish to express my gratitude to Dr. Bikash Chandra, sir, for providing encouragement at artifact removal of EEG signals using machine learning techniques. So thank you, sir. It was very effective session. Thank you, sir.
Thank you, Dr. Rasid and Dr. Ram Kumar, for giving me opportunity to interact with the faculty members in this FDP. Thank you.
Thank you. So there is a 10 minutes break. After 10 minutes, we will start the next session. Thank you.